Okay, I'm gonna write something in. So here, what about here?
Check.
That's good.
I mean, it's not going to be especially good picture quality, probably, but
Yeah.
just because it's. Although it might be better once it's
You can move
on a
things
big screen.
around to, yeah, maybe it will.
But I can see there.
There.
You're just off.
I'm just off here.
Right there. Yeah, that one's off.
Okay.
Also, if you flip the camera,
I can't
the other
actually
way,
see that line,
it'll
but.
be a better picture if you upload it.
Oh, yeah.
I
I don't think I can stabilize it though that way.
Take away the water bottle, just use the calculators.
No, I don't think, because even the calculators, if it's on its side.
You want me to try it?
No, this is good. This is good.
Okay.
Yeah. Well, you can give it a quick try. Give it a quick try. I don't want to take more than one more minute on
Yeah.
this. Oh, I see. Yeah, the camera up the other way. Duh.
Yeah.
Hey, geometry. Look at us
Although
go.
it's very low now.
Very low.
Let's see. I think I can just about. There we go.
All right. And can you read it over here? Okay.
Yep.
All right.
I can see almost the whole board. There is the way it's set up. There's kind of a.
So right where that line is, pretty much.
That's about here, but I can see here.
Okay.
basically.
Cool.
Lights, camera,
Action. All right. Hello, everybody.
Did you
Oh,
hit
those are
record?
both really good. All
Did you hit record?
right.
It's been recording.
Oh,
Yeah. I think. Yes.
That'll work. That'll work.
Pretty certain I didn't stop it. Maybe I'll just double check that.
So I'll leave that there and that there, and we'll get started. I will pass out the. Somewhere very close to me. Where are you, signing sheet? There you are. All right. So normally I'm going to be reading names out loud and doing all the fun things for about the first 2 weeks. But because I kind of want to get through the review and get started into new material, I'm just going to send that around. So be sure to send in, or be sure to sign the sign-in sheet before you leave today. Can you see okay here? Everyone can see okay? All right, well, welcome to class 2 of 254. We're going to go through the review stuff from 12, 3, 4, and 13.1 today. So some folks haven't had chapter 13, so I'm going to review that and do it. I'm going to be doing 13 as we go, but yeah.
What class is this?
Sorry, oh, when did you do chapter 13? Or
What class is
this? Math 254. Yeah? You're in the wrong one? Everyone here is for Math 254, right? Calc 4? Yeah. What are you supposed to be in?
Psychology?
Psychology? Oh. We can describe psychology using mathematical equations. Oh, okay. All right. All right. Is everyone else here for Math 254? Awesome. Cool. So here we go. All right. So you guys are going to know all about this, the dot product. Let's see. For the rest of the day, pretty much, I'm going to use 3 vectors: u, v, and w. And they're going to be with entries u1, u2, and u3. And no surprise, v1, v2, and v3. And w on w2 and w3. So this is our main cast of characters. We have these 3 vectors. So given these vectors. So they're our friends, they're what we're going to play with. Given these vectors, the dot product of, let's say, v and w is denoted, as we know, with just a kind of solid dot, v, solid dot w, and is given by a formula, which is v dot w, that's not w enough, equals V1, W1, V2, W2 plus V3, W3. And all familiar, you multiply the components and sum them all up. Just for this one split second, I'll just reintroduce to your mind sigma notation, which is a summing notation. So we sum over an index. Here it's going to be the index 1 to 3, and we'll do VI, WI. That means component VI, the ith one, times the component VWI, and adding it all up. So all that notation is clear. Everyone's good with that? Great. We have some properties that we've discussed a little bit and we've seen are intuitive for the most part, or pretty easy to see. One property is that I take any vector I have times the 0 vector, I get the number 0, right? If I multiply each component by 0 and add them up, I still get 0. If I take the dot product of V and W, I'm multiplying the components together and adding them up, but the multiplied components commute, right? So since the multiplied components commute, the multiplied components can be switched, I can switch the whole dot product. So the dot product is commutative, right? Okay. And 3, if I have a constant times V, one vector, and I dot it with W, I could easily pull that constant out of the whole thing. So say I had a constant times a vector, and then I took the dot product of that constant times a vector with another, I could have just done the dot product of the two vectors and multiplied by the constant later. All pretty reasonable. And finally, 4, the one that may take a little more thought, but should seem pretty reasonable ultimately, if I have a vector U dotted with the sum of two vectors, then the dot product distributes over that sum, just like A times something in parentheses distributes over those two. All right. So this all seems pretty intuitive, pretty reasonable, and we're just going to say, yeah, it does all these things. If you wanted to check for yourself, you could plug in these vectors and just do a little bit of algebraic manipulation with symbols, and you could convince yourself of it. And I trust that you could do that. But it's not the most important thing right now. I want to note too, let's think for maybe a split second. Given this, we can actually extend this to foiling. So note, for implies we can foil, right? It implies we can foil. If this were, let's do U plus V dot W, and we'll do another vector Q. If I have this, right? Well, this is a vector and this is a vector, right? I could just relabel this as a new vector. Let's call it U star, right? This whole sum of two vectors is again a vector. So using this then, with U star in here, I can distribute this U star onto W and Q, right? So that equals U star dot W plus Q, right? So just replacing this whole guy and seeing it as one vector, I can apply this rule twice, and I get foil, right? Yeah? That cool nodding head worthy? Okay, great, cool. So foil is good, and last thing before we do our first proof, recall the length of a vector. So the length of a vector V denoted, what's the denotation for length of a vector?
Two brackets around.
It's double brackets, yeah. So it's like the plane coming onto the field. It's like 2 bars. Denoted double bar V, yeah, like we said, is given by So in 3D, you might not think the Pythagorean theorem would hold, but it does. It's just another iteration of the Pythagorean theorem. So the length is the square root of the components squared and summed together. So maybe we take a quick look at that. Let's say I have a vector coming up here to a point up here, and it goes down. Here's the shadow of the point, and we want to know how long this is. Yeah. So this V1 component, V2 component, and V3 component. And this formula says that it turns out that this length here is just the square root of the sum of this length, this length, and height. Yeah? Yeah.
So we're not calling that the norm?
We could call it, it's a norm, so we're not calling it the norm per se.
Okay.
Yeah, I could refer to it as either the norm or the length.
Okay.
Yeah, yeah. So if you have heard of this as the norm of a vector, it is the norm of a vector. It's one norm of a vector. But the reason I call it length is it just, there are different kinds of norms, and this is very suggestive of what this actually is. Yeah.
So the norm is basically just a more generalized term of length. You might want to use norm in cases where you're not dealing with length as or any specific size or geometric quality.
I think of norm as a way to associate a real number with something that isn't real. Actually, yeah. And generally, it's always positive as well. So it associates a positive real number with a vector. That's a general norm. Here, this is a specific norm, right? I could have taken the length of the, not the length of the vector, but I could get a number out of a vector just by making these positive and summing them up, something like that. So this is, in particular, a Euclidean norm, and hence I'm going to call it length.
So for like non-Euclidean geometry, you might want to use a different norm.
You'd have to. You better, or else it's all going to mess up. All right, so this is length, and hey, look at this guy here in the middle. We also have, now, we have an easier way of writing length. We also have that the vector v dotted with itself is what? Well, it's multiplying the components and adding them together, so we have v1 times v1 plus v2 times v2 plus v3 times v3 is v dot v. And so v dot v is actually equal to, well, the length squared. So that's another handy formula we want to have on our hands. Well, hey, tricky. Okay, so with that in mind, how am I looking?
You know, actually part of the screen is obscured by how, part of the screen on the phone is obscured, but I think you're okay.
Okay, all right, I'm hoping I'm okay. So with all this in mind, we have theorem 1, which is, let theta be the angle.
Oh, you can't really see that high up there.
Oh, can't see that high.
It's cut off.
Where does it get cut off?
You can see the theorem 1 part, but you can't really see the let theta be.
Oh, interesting. So it's not height, it's to the right?
It's at a diagonal.
Just drag it.
Yeah, what if you move the camera over?
Well, where is it? How's it doing?
Looks good.
Okay, good. From here on out, I won't concern myself with it too much. If it's off, I want to get you guys the information. I can scan these notes and tell people to look at them. So, yeah. So theorem 1, let theta be the angle between two vectors. We're going to do v and w. Then we have a relationship between angle and dot product pretty quickly. We have the dot product of v and w